Hello, welcome to everyone in this video. This is lecture number 11 on solid state physics. Today we want to discuss about the Clausius Mosotti equation. Okay, you can see this is the syllabus. This portion 1 crystal structure, elementary lattice vibration, magnetic properties of matter. These three part already discussed. In the last lecture we discussed about the polarization, local electric field at an atom, depolarization field, electric susceptibility and plausibility. Today we want to cover up this portion, that is the Clausius-Mosotti equation. In the upcoming lectures we will be discussed in the upcoming portion of this syllabus, right? So let's talk about this Clausius-Mosotti equation. Actually, this equation is the relation between the polarizability and the dielectric constant. Actually, polarizability is the microscopic property of this material, but the dielectric constant is the macroscopic property. So you can see this is the relation between the microscopic property with the macroscopic property. You are all very know about these two terms, microscopic property and the macroscopic property, from the statistical mechanics. So you understand what is the meaning of the microscopic and macroscopic properties. And the polarizability is the microscopic property, small region property, but dielectric constant is as a whole of this material property, that is the macroscopic property. And this Clausius-Mosotti equation is like that, where the epsilon r, that is the dielectric constant, is minus 1 by plus 1 is equal to n alpha by 3 epsilon naught. This is actually the Clausius-Mosotti equation, and this relation between the macroscopic property and the microscopic property, where epsilon r is the relative permittivity or the dielectric constant, n is the concentration of atom, and epsilon r the permittivity in the space. Alpha is the plausibility. If we want to derive this relation, we need to know about the local field. In the last lecture, we discussed about the local field, that is the small region electric field. This actually depends on this fourth term, that is the external. E naught is the external electric field. E depolarization, you know about the depolarization field, where the surface charge opposed to the applied field, that is the depolarization. That's why this negative sign arises here. And EL is the Lorentz electric field. This is the positive part of this one, and this P is the polarization, and E deep, that is the field at the center of the cavity of dipoles, that is the dipole electric field. So finally, the total local local electric field will be like that. Macroscopic field, you can say that in this there is a macroscopic field, that is E naught, and the polarization, that is the external field, and the polarization field are the macroscopic field, and this is the average field experienced by the dielectric constant over the sample dimension. And microscopic field is the E vector and the P by 3 epsilon. This relation actually known as the Lorentz relation. Now this dipole moment is alpha E local, which is the B is the electric dipole moment. So the total polarization is the summation of this total dipole moment with the number of dipoles. You know this displacement vector d vector equal to epsilon E plus P. P is the polarization, and also displacement equal to epsilon E. And if you compare these two things, will be obtain the expression of the polarization like here. Hence, the local electric field is E plus P by 3 epsilon naught. You can see here, E local equal to E plus P by 3 epsilon naught. Put this value of P here, you will be obtain this expression. And this polarization P vector equals to summation of this one, because this small p is nothing but the alpha E local. So, jth component actually. So finally, this will be obtained, and this is nothing but chi E. Chi is the susceptibility, and you know this total polarizability will be like that. So if you compare this thing, you will be obtain this relation, which is Clausius-Mosotti relation. Now, actually, in the first relation, we write down in this error. Actually, this will be 2. I need to correct this one. This one will be 2. Okay. So will be obtained this Cauchy-Mosotti relation. Now, this relation actually valid for dielectric having cubic symmetry. Dielectric with the cubic symmetry for this relation is valid, and polarizability has the electronic component only. That is the polarizability of the three component ionic polarizability, electronic polarizability, and atomic polarizability. So, this is only electronic component, and this will be the expression. Where m is the molecular weight, n is the Avogadro number, rho is the density. If you consider this as a x, so x is nothing but 1 by 3 epsilon naught summation of this one. Just expression, just rearranging them and expressed, you will be obtained finally epsilon r equal to this one. In case of gas or atomic molecular density is very low, so local field correction will be neglected. So finally epsilon r will be this one in case of the gas. At optical frequency, electron polarizability overcome the dipole ionic contribution due to inertia of the molecular this relation, that is the relative permittivity, is proportional to n square, so then this relation will be like 1, and this is known as Lorentz formula. So I think clear about this relation and their corresponding. This is all about me. This is my contact detail. You can connect with this Telegram channel, and this is my YouTube channel details. Go to this channel. We get different related video, some mathematics. Like this session. If you learn something from this session, share this video to your friends so that he or she also get benefit from this video. Subscribe the channel if you new in this channel. Those already subscribed, thanks for subscription. Press the bell icon to get notification of upcoming videos. So take care. We'll meet in the next video as well. Thank you.